Oscillations are happening all around us, all the time. In fact, even the atoms that make up you and me are oscillating right now. Simple harmonic motion is a special type of oscillation where the amplitude is proportional to and the direction is opposite to the displacement from equilibrium position. Let's have a look at some common examples. Here I have a simple pendulum. It consists of a string and a mass. Whilst in equilibrium position, we can measure the length. In simple harmonic motion, the quantity of interest is period, the time for one oscillation. The period is given by 2 times pi times the square root of length divided by gravity. In our case, we expect the period to be 1.55 seconds. If we displace the mass by a small distance, we initiate the simple harmonic motion behaviour, and then we can determine the period. After allowing for some time for the pendulum to stabilise, we can start timing. For accuracy, I'm going to time 10 full swings. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the time for 10 oscillations. For one period, we need to divide it by 10. We'll also repeat this 2 more times for accuracy. From the equation of period, we can see that it's related to the square root of the length. This means that if we quarter the length, the period halves. And we see that this is the case. Notice that the period is not dependent on the mass, so adding more weights shouldn't make a difference. The inverse of period is frequency, or the number of oscillations per unit time. In our original case, we measured 0.63 oscillations per second, or hertz. Now, let's do it again with a simple spring. Here we have a spring and a mass. The period is given by 2 times pi times the square root of mass divided by the spring constant. That's a measure of how stiff the spring is. Again, I would displace the mass by a small distance and let it stabilise before I start timing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll repeat that again 2 more times for more accuracy. This means we get a frequency of 1.7 Hz. To get the spring constant, we need to rearrange for K. Unlike the pendulum, we could quadruple the length, but that wouldn't change the period. However, if we quadruple the mass, the period would double. In everyday life, simple harmonic motion is all around us. Everything from wind turbines to car suspensions and even electric motors. Here at the University of Birmingham, pendulums and springs are important for our research projects, such as our role in the detection of gravitational waves. Here I have a damping system, which helps to stabilize oscillations and allowed us to make the first detection of gravitational waves.